Thank you. Thank you, and good evening, Southport, once again. Yes, this is the end of everything. As you can see from the subtitle, I'm talking about the fate of the Earth and the fate of the Sun and the fate of the galaxy, and ultimately the fate of the universe. So probably the most depressing talk you're going to listen to for the entire season. So what we're going to do, if you excuse me paraphrasing our old friend Buzz Lightyear, we're going to go to eternity and beyond. So we'll be, after a little prologue, we'll be looking at the future of what's in store for the Earth and the Sun and possibly the rest of the solar system. We'll be looking into the far, far future of what's going to happen to the stars in the Milky Way and other galaxies. And we'll be looking into the far, 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 far future of what ultimately is going to happen to the universe. In order that you don't leave totally depressed, I will finish with a little epilogue to try and finish on a slightly more upbeat note. So, a long time ago, I looked it up. Back in 2011, I talked about the beginning of everything, how the universe came into being. I'm not going to recap that particular lecture. But ultimately, the bottom line is, well, the universe is expanding. And so we can say if it's expanding now, then it must have been a lot smaller in the past. And we can calculate that everything that we now see in the observable universe, which is a huge sphere, 100 billion light years in diameter, if we wind the clock back far enough, we find that everything inside that sphere was an awful lot closer together, only centimeters apart, which is a mind-boggling idea. So the universe started as a very small entity and has been expanding ever since. And along the way, it made all of the hydrogen, which ultimately has fueled all of the stars, including our own sun. But here, we're not dwelling on the past and how we got to be where we are 13.8 billion years after the Big Bang. We're asking what happens now, what happens in the future. And in order to keep track of where we are, I've got a timeline running along the top. There's no point in going in years or even millions of years. We have to keep going on an exponential scale, and to keep track of where we are, these are the powers of 10 that we'll be dealing with. In other words, each box at the top there corresponds to 10 times further into the future than the previous one. So we can think about, for instance, 1,000 years into the future, 10 to the power 3. We can go to 10 to the 6, 1 million years into the future. 10 to the power 9, 1 billion years into the future, or 10 to the power 12, a trillion years into the future. So that red rectangle will move along that line to sort of keep track of where we are, hopefully to make it a little easier to keep track of how time is flowing. But also, if you look at one of the handouts that I'll make available at the end there, again, that red box will remind you, if you're looking at a particular part of the handout, a particular slide, where are we on this future timeline. So the obvious ones are 10 to the 3, 6, and 9, the 1,000, million, billion, at the end there, trillion. But of course, the red box will move square by square by square. I'm indebted to these individuals. I'm not going to dwell on this, but a paper was written 25 years ago, in which they calculated the timescales on which various astrophysical phenomena are likely to occur. And I've used that paper as a guide to try and get my slides in the right order, because I want to move chronologically. Even if I jump around from the Earth to the Sun to the galaxy and back to the Earth again, I'm trying to keep it all on a chronological timeline. I'm not going to start 10 years into the future or 100 years into the future. Let's assume we don't have a nuclear war. Let's assume we get climate change under control. Things start to get interesting if we go a few thousand years into the future. We know that the Earth's spinning and its axis points to a particular part of sky, and we know that the Earth's axis precesses. In other words, the Earth's axis sweeps out a big circle on a timescale of about 26,000 years. We know most of these numbers simply from looking at historical records. So what's the consequence of the fact that the Earth's axis points to different parts of the sky on a cycle of 26,000 years? At the moment, the Earth's axis, of course, is pointing at what we would call the North Celestial Pole, which happens to be close to the star Polaris. That's quite handy. We've got a reasonably bright star close to the pole. Not particularly bright, so Boy Scouts still have a problem sometimes picking out Polaris in the night sky. But in half of 26,000 years, the North Pole will be pointing in a different part of the sky. It will be pointing the other way, if you like. And the North Pole will be closer to the very bright star Vega. So what's the consequence of the pole star changing like this on a timescale of about 12 to 13,000 years or so? Well, there's a couple of consequences, but one that might be rather important is, at the moment, we're in the situation we see on the left-hand side. We are nearer to the sun, perihelion, because of the Earth's orbit being an ellipse, not a circle. We are actually closer to the sun during northern winter. So that partly mitigates the fact that we're colder because we're tilted away from the sun. But when the Earth's axis is pointing the other way towards Vega, we'll be nearer to the sun during northern summer. So it'll exacerbate the seasons. The seasons will be more exaggerated because of this particular effect. And that collection of variations to the Earth's climate as a function of the way the Earth is spinning or the way the Earth is going around the sun, these cycles, these changes to the Earth's climate as a function of the astronomical changes to spin and orbit, those are collectively known as Milankovitch cycles, and we'll see those later. Of course, the other consequence is, because Vega is a very bright star, it'd be much easier for Boy Scouts to point out which way is north. Okay. On a timescale of 10 to the 5 years into the future, 100,000 years into the future, various space probes that we've launched in the past will start reaching other stars. So Pioneer and Voyager spacecraft, which went past Jupiter and Saturn, and in the case of Voyager, Uranus and Neptune as well, before leaving the solar system, on this timescale, they'll be visiting other star systems. They will have left our solar system completely and will probably be passing through the first or the second solar systems on their way. So we don't need to worry about exactly what orbit they're on, but this is the Voyagers that were launched in the 1970s. They were launched at roughly the same time, but they had different tasks. One went to Jupiter and Saturn, the other carried on to Uranus and Neptune. So they're actually heading out in different directions. At the top there, Voyager 1 is heading off in the direction of the star system called Gliese 445. Down at the bottom of the picture, the Voyager 2 is heading off in the direction of the star system Ross 248. Launched in a similar time, a little earlier than the Voyagers, were Pioneer 10 and 11. Pioneer 10 is heading off in the direction of the star Aldebaran, and Pioneer 11 is heading off in the opposite direction towards the center of our galaxy. They will take a little longer to reach star systems just because they're traveling a little more slowly. But all of these things will happen on timescales of order 100,000 years, maybe 40 to 50,000 years or so. Now, ice ages will come and go, and again, on a similar timescale of 100,000 years, we're due for the next ice age. We know that ice ages come and go on timescales of 100,000 years or so. We see that in the records. When we look through the sedimentary record and the fossil records, we see that ice ages come and go every 100,000 years or so. And we know that Earth entered a relatively warm phase of the ice age cycles relatively recently. So in other words, the next real ice age is due on this sort of timescale. So we can predict, not absolutely accurately, but we can predict that the next ice age will come along in about 100,000 years or so. Why is it so regular? Again, it's another manifestation of what we call the Milankovitch cycles. It's a function of how the Earth's orbit is changing around the sun. A little while ago, I talked to you about how a second is defined and why we need leap seconds. I gave you the talk, I think it was last year, was it? Just a second. And I talked about how the Earth is slowing down, and hence, every once in a while, every few years, we put in a leap second to correct for the fact that the Earth's rotation is slowing down because of the tidal effects of the moon. Now, in 100,000 years or so, the Earth will continue to slow down, and those leap seconds will need to be added, not necessarily once every year. We would need to add a leap second basically every day. So in other words, the 24-hour of the Earth's rotation at this point will be more like 24 hours and a second. We will have to keep adding a second every day, not wait every year and add a few leap seconds at the end of the year. And this will continue for the foreseeable future. Stars are going to evolve. And again, on a timescale of 100,000 years, it is quite likely that we will see some stars go supernova. Some massive stars coming to the end of their lives will explode and produce a rather spectacular sight in our sky. This particular one, Eta Carinae, is actually in the southern hemisphere. It can't be seen from England, but we know that that star is unstable because this nebula that you can see around the star is the result of the star shrugging off its outer layers. It's been doing that for thousands of years, and the nebula that's produced is the result of this star being rather unstable and finding it difficult to hang on to some of its outer layers. This is a sure sign that this star is getting very unstable and could be the candidate for the first star to go supernova in the next 100,000 years or so. It's notoriously difficult to try and predict when they're going to go off, but almost certainly it'll be on this timescale. It might be beaten to the punch by this one, Betelgeuse. You can recognize, perhaps you can recognize the constellation of Orion, but Orion is going to get very distorted if Betelgeuse in the top left-hand corner there goes supernova. So this is a genuine picture of the night sky, but with Betelgeuse artificially brightened to give us an idea of what it will look like. Not only will it be very bright in the night sky, it'll be visible during daylight for quite some time because Betelgeuse is not that far away from us. So whether Betelgeuse goes first or whether Eta Carinae goes first, it's very difficult to say. On a timescale of 10 to the 6 years, we know that all the stars are rotating around the center of the Milky Way. Our sun takes a few 100 million years to do one orbit around the Milky Way, but all of our neighbors are doing the same thing. All of the stars in our neighborhood are all orbiting around the Milky Way, but they haven't all got exactly the same period, so some stars might tend to come a little bit closer to us, other stars might drift away from us. In other words, our immediate neighborhood of stars is not absolutely fixed, not on this timescale. On a timescale of 1 million years into the future, by calculating how stars close to us are moving, we can calculate that one star in particular is actually going to get very close to us. The star Gliese 710 is actually going to get so close, it will actually come inside the Oort cloud. The Oort cloud, a large cloud centered on our own sun with trillions of icy particles. These are the ones that are responsible for comets, including the comet that's been gracing our skies for the last few weeks. So what's going to happen when another star comes within the Oort cloud? It's going to disturb the Oort cloud because most of these icy particles are sitting in this large sphere and are very weakly gravitationally bound to the sun. Bring in another star, it's going to disturb the Oort cloud, and what that's going to mean is that we're going to get, I don't know how many comets coming into the inner solar system. It's been calculated that when we disrupt the Oort cloud because of the arrival of this star, we could probably get in the inner solar system naked eye comets perhaps once a month for 1 million years, for as long as it takes Gliese to come close and then drift away again as the two orbits independently move around the center of the Milky Way. So it's interesting to note that for a short time, we're actually going to have 2 stars in our solar system. Our solar system will have 2 suns, just like other places that you've probably heard of as well, like Tatooine from Star Wars. It won't quite be like that because this star will not be as bright as the sun. These two look very similar brightness. Gliese 710 will be quite dim because it will still be quite some distance away, but we will have 2 stars in our solar system. Still on a time scale of 1 million years. Is this supposed to indicate that we can expect an impact like Meteor Crater Arizona? Can we expect one of those every 1 million years? No, that's not why this photo is here for 1 million years. One, we note this particular impact, wasn't it a stroke of luck that it just missed the visitor center? I mean, what are the chances of that? I mean, yeah. No, the reason this is here at 1 million years is we can expect that although there will be lots of these over 1 million years, the Earth's atmosphere will get rid of any signs of impact because of weathering, because of wind and rain and erosion. This exists because it's not that old. But if we had a similar impact many millions of years ago, its trace would have been probably wiped clean because of the effect of the Earth's atmosphere on typical timescales of 1 million years. So you might say, well, okay, that's true for the Earth, but it's not true for the Moon. Things will last forever on the Moon because there's no weathering, because there's no atmosphere. Well, it's true there's no atmosphere, but that doesn't mean that things will last forever, because the moon is being pulverized by a continuous rain of micrometeorites. So it's not rain in the sense of our atmosphere, but there are micrometeorites hitting the surface of the moon, which means even things like, for instance, the Apollo footprints will not last forever. After this sort of timescale, the surface regolith, the surface soil, if you like, will be pulverized by micrometeorites to the point where there'll be almost nothing left. Even the Apollo hardware itself, if you wait long enough, will disintegrate under the micrometeorite rain that's continually raining down on essentially all bodies in the solar system. We just don't notice it on Earth because we're protected by an atmosphere. On a timescale of 10 to the 7 years, so now 10 million years into the future, things are going to happen to the Pioneer 10 plaque. The plaque is the plaque that identifies where the probe came from. It was sent out and is leaving the solar system. Remember, it's likely to pass through other solar systems on timescales of 10 to the 5 years or so. So after 10 to the 7 years, it will already probably have passed through hundreds of different solar systems. But on this timescale, things are going to happen to the plaque that allows people to identify where the probe came from. If you remember what the plaque actually signifies, humans on a scale to the probe itself, a pulsar map saying this is where Earth is, and a little schematic of the solar system saying this craft came from the third rock from the sun. So if you can read this plaque, you can work out where its origin was. But after 10 to the 7 years, this plaque will become essentially unreadable, because Pioneer 10 is flying through the interstellar medium, and the interstellar medium is not empty. It's full of tiny particles of dust, effectively what the micrometeorites are that are raining down on the moon. So there might only be tiny particles of dust, but if you fly for a few million years, eventually they are going to pit and corrode and erode the actual plaque itself. And so that is going to become unreadable. So if Pioneer, either 10 or 11 is picked up on a timescale of 10 million years after passing through various solar systems, then perhaps some interesting extraterrestrial intelligence is going to pick it up, but at that point they would not be able to figure out where it came from. On a timescale of 10 to the 8, 100 million years into the future, we can ask what's going to happen to things in our solar system. For instance, what's going to happen to Saturn's rings. But perhaps before we ask what's going to happen to Saturn's rings, we ought to ask where they came from in the first place. It is thought that perhaps Saturn's rings were made by a moon either not forming or a moon that formed and then was pulverized, perhaps with a collision with another moon or perhaps with a collision with a comet. If you take a moon about the size of Mimas, that's Mimas there, you look at a moon like that and you might think to yourself,
that's no moon, it's a space station.
Because it does bear an uncanny resemblance to the Death Star. But it's thought that if you take a moon like Mimas with that much mass, if you pulverize it, what would happen to the debris that was produced? You might think, well, you know, you'll end up with a cloud of debris and that will go round Saturn much like the moon originally did. But a simulation was run to see what would actually happen if you take Saturn with no rings and you take a small moon like Mimas, pulverize it, and then basically sit back and wait and let gravity do its stuff and see what happens. What happens is quite surprising. It doesn't simply go round as a small cloud. Look at the timescale in the bottom right. How long does it take until a ring system actually forms? It is hours or days for the debris to spread itself around the entire orbit. So it's a bit counterintuitive. You think it might just simply go round as a cloud, but in fact it forms a ring system in a matter of days. And it can be calculated and shown that what's actually happening to each individual particle in the ring system is that they are slowly spiraling inwards because they're interacting with each other. If it was just one particle in orbit, it would just stay in orbit. But because there are trillions of these tiny things all bouncing into each other, they are slowly spiraling in and ultimately raining down onto the surface of Saturn. So millions of years later, we end up with this beautiful ring system that we see today. But the process hasn't stopped. The individual particles in the ring system are still spiraling inwards, and so ultimately everything we currently see in the rings will eventually spiral in and rain down onto the surface of Saturn. So on this sort of time scale, we can wind the clock forward and we can say the rings of Saturn will disappear. So those of you who like to look at Saturn through a telescope, get in now, because in 10 to the 8 years, you will not have that spectacle anymore. Still on the same time scale of 10 to the 8 years, I've told you about the Star of Bethlehem and how we can work out where the planets are now and how the planets are moving, and we can wind the clock back if we want 2,000 years and ask what was in the sky 2,000 years ago. Where was Jupiter? Where was Saturn? Were they in conjunction, etc.? We can do that with phenomenal precision. But we have to remind ourselves that although we tend to think of the solar system as being clockwork, and we can sort of treat it as clockwork for a while, certainly thousands of years, tens of thousands of years, hundreds of thousands of years, but ultimately on a time scale of 10 to the 8 years, the solar system is chaotic. In much the same way that you can work out what the weather is going to do in terms of a storm is coming, so we can work out that storm will arrive tomorrow, but we can't work out what's going to happen in 1 month's time. It's predictable a certain distance into the future, a certain time into the future, but it's completely chaotic on longer time scales. It's the same for the solar system. We know pretty much what's going to happen on short time scales, but on time scales of many, many millions of years, it is totally chaotic. Not only can we not tell where Jupiter is going to be in its orbit, we can't even tell how many planets we're likely to have in the solar system on this timescale. It might be that Jupiter has decided to throw out one of the smaller planets. It might be that some planets have decided to rearrange themselves. We think that's happened in the past. It could happen in the future on this sort of timescale. When systems are chaotic, you simply cannot predict what they're going to do. That's something to bear in mind when we're thinking about trying to make predictions for the future. Still on a timescale of 10 to the 8, 100 million years, this is the timescale, roughly speaking, of how long it takes the sun to go around the Milky Way. It takes probably a couple of 100 million years for the sun to do one orbit. At the moment, that's where we are. We are sitting, roughly speaking, in between two relatively highly populated spiral arms. We're sitting in a little bit of a backwater, a relatively underpopulated part of the Milky Way. In other words, we don't have that many stellar neighbors. But on a timescale of 10 to the 8, it's been calculated that we are going to move inside one of these spiral arms, which means we are going to have a lot more stellar neighbors on this timescale. In 10 to the 8 years' time, we are likely to have many, many more neighbors. If you think about how many stars we have at the moment, within 10 light years, there's only a few. But on this sort of timescale, we might have dozens, if not hundreds of stars within a few light years of us, or at least 10 or so light years of us. So what's the consequence of having a lot more stellar neighbors, apart from the sky looking rather prettier, because we're going to have more stars in the sky, more naked eye stars? Well, there are two consequences of having a lot more stellar neighbors. One, we've already sort of thought about. What happens when a star like Gliese 710 gets too close? It intercepts the Oort cloud. It interrupts the gravitational stability of the sun acting on the Oort cloud. It results in lots of comets coming into the inner solar system. So when we've got a lot more stellar neighbors, that's likely to happen a lot more often. And on this sort of timescale, we can expect to get a lot more things raining down on the Earth. And if we look at extinctions as a function of time, this is what percentage of species were made extinct as a function of when. This is now on the right-hand side, 100, 200, 300 million years ago. So it's 500 million years or so of history. We get that by looking through the fossil record. We find that there have been mass extinctions, and there's been 6 of them in the last few 100 million years. It's not regular as clockwork, but it looks like every few 100 million years we tend to get a likelihood of a spike. The last one, the KT boundary, that's the one that killed the dinosaurs. It's the boundary between the Cretaceous and the Tertiary eras. That was a relatively small body, only a few miles across, but that was enough to kill the dinosaurs, which is just as well because it left those small mammals to evolve into us and a few other things as well. So we don't absolutely know. Some people would question whether or not this is a causal relationship or whether this is coincidence, but it looks like extinction level events happen on these timescales, and we definitely have more stellar neighbors. on these time scales. And so it is quite likely that a very large chunk of rock is going to come our way on this sort of time scale. Again, we can't predict when. We're simply saying on this sort of time scale, it is very likely to happen. So this is clearly an artist's impression of what might happen. A large chunk of rock is heading towards the Earth. From the looks of it, it looks like Italy is in for a bad day. Now, of course, if Italy's in for a bad day, it's not just Italy. It's bad news for the entire planet. If a large enough rock hits it, there will be extinctions. This will be possibly an extinction level event. Species will become exterminated. The only real question is not will it happen, is will it include us? If we can perhaps do something to try and mitigate that, either by getting Bruce Willis to move it off its course so it doesn't hit the Earth, or we need some other mitigation strategy to try and survive an impact like that. Still on a time scale of 10 to the 8, because it's still another consequence of what if we have lots of neighbors, some of those neighbors might go supernova. At the moment, there are no stars close to us that are massive enough to go supernova. You need a relatively massive star to burn its fuel really quickly before it will explode as a supernova. But if we have a lot more neighbors, perhaps some of those neighbors will be very massive stars, and hence we might get a supernova going off quite close to us. A supernova going off 1,000 light years away is not a problem. A supernova going off next door could be really bad news. So again, this is only an artist's impression. So the idea of a star going supernova and then cutting a planet in half, well, it's a nice bit of artistry, but will that actually happen? But we know a supernova going off, we can calculate the effect of what it would do. We know that a supernova going off within 100 light years of Earth would be really bad news. It would be a danger to Earth. The gamma radiation from the supernova would cause a serious hazard to life. If we had a supernova going off less than 20 light years from Earth, it's been calculated that that might end all life on Earth because of the radiation. 20 light years is simply too close. And if that sounds a bit crazy, that surely that will never happen, well, we know that the historical records that tell us supernova have gone off relatively close to us in the ancient past. There's a particular isotope generated by supernova. It's called iron 60. Iron 60 is an isotope that's not made naturally, so it doesn't occur on Earth naturally, but it's made in supernova because of the energies involved when a star goes supernova. It can make this particular isotope. And the isotope is radioactive in the sense that it's unstable. It starts off as iron 60, but then it changes into cobalt and then changes into nickel. So the nucleus of this atom will change from iron to cobalt to nickel. And we know, roughly speaking, the time scale on that will happen. It's many millions of years. But that means that if you find any iron in the Earth's sediments, it can't have been there for billions of years because this radioactive process will change iron into other things. And we look in Earth sediments, and what do we find? We do find in Earth sediments iron 60. The only way it could have got there, as far as we know, is from a supernova that sent it out into the void and some of it landed on Earth. It is not left over from the Big Bang. It is not left over from when the Earth was made. It must have arrived relatively recently because it would otherwise have changed into something else. So we deduce that there's enough of it that the supernova must have been quite close. If it was really a long way away, we wouldn't see much of this isotope in the soil, in the sediment. So we deduce that we have had neighbors in the past which have gone supernova. If it's happened before, it can happen again. Still on a time scale of 10 to the 8, we're not quite done with that exponent just yet. Still 100 million years into the future, we know that the Earth and the Moon will continue their little dance of the Moon raising tides on the Earth and slowing the rotation of the Earth down. So remember, we currently have leap seconds once every few years. We haven't had a leap second for quite a few years now. I said before we would need to add a leap second every day. But on this time scale, because the tidal friction of the Moon raising tides on the Earth, in other words, robbing the Earth of some of its angular momentum, the Earth is slowing down, the spin is slowing, and the Moon is taking that angular momentum and increasing the size of the Moon's orbit, the length of a day for the Earth is now 25 hours. The idea of leap seconds has gone out of the window completely. No amount of leap seconds is going to keep your 24-hour clock synchronized with the rotation of the Earth. This is a good time to decimalize. To hell with 24. Yes, it's got some good factors in it, but at this point I think you want to say, well, there are 100 quarter hours in the day. Let's start decimalizing it. Apart from the fact we have to really rethink our clocks, there's another consequence of the fact that the Earth is slowing down. It's because the moon's orbit is increasing. And there's more than two consequences, but there's two consequences I want to think about. With the moon moving further away, it means we're no longer going to be able to see a total eclipse of the sun, as we have been able to see for generations past. In the future, because the moon will be further away, the distance from Earth to the sun won't change that much, but if the distance from the Earth to the moon increases substantially, the moon's disk will no longer be large enough in the sky to cover the disk of the sun. So all we can look forward to in the future is either a partial eclipse or perhaps an annular eclipse where the small disk of the moon is not large enough to cover the sun and you're left with a ring of fire around the outside. So again, for those of you who like to go around the world watching total eclipses of the sun, get your tickets in now, because on a time scale of 1 billion years or so, the moon will be so far away it will not be possible to see a total eclipse from the surface of the Earth. But perhaps a more important thing, other than to the chagrin of photographers, a more important consequence of the moon moving away from the Earth is the fact that for a long time now, the moon has been stabilizing the spin of the Earth. The Earth's axis is tilted by 23 degrees relative to the normal of the plane of the orbit around the sun, the so-called ecliptic. And that tilt of 23.5 degrees hasn't changed much. It hasn't changed by more than about a degree either side of 23.5, which is roughly speaking where it is at the moment. In other words, that cartoon on the left, the Earth is actually nodding backwards and forwards, but you can hardly see it because the difference between 22.5 and 23.5 and 24.5 is hardly visible. The seasons haven't really changed that much in a long, long time. However, if the moon moves further away, it's been calculated if the moon moves something like an extra 25% further away compared to what it is at the moment, then it will not have the stabilizing influence. In other words, the angular momentum of the two systems won't couple together, which means the Earth will hardly be aware of the fact that the moon is there, and the Earth's tilt will be able to wildly go backwards and forwards. It'll no longer be pinned, if you like, because the Earth and the moon are coupled together by the mutual gravity. Once they're further apart, the Earth's axis could, in principle, change erratically. And of course, if the Earth's axis changes, that means the seasons are going to be all over the place. So again, nothing periodic about this. This is more likely to be a chaotic transition to seasons which are basically no longer seasons, because we no longer have a fixed tilt as we go around the sun. The Earth's axis will be going all over the place. So who knows what's going to happen to the Earth's climate on this sort of scale. 10 to the 9, we're still on 10 to the 9, 1 billion years into the future, and I'm coming back to Voyager again. Voyager, a little like Pioneer, which has got a plaque on it to say where it came from, the Voyager spacecraft, they were a little more ambitious. They wanted to include a gold disk, a gold-covered copper disk. And it's a phonograph, basically, with sounds of Earth and messages of welcome and peace as we go into the cosmos. So again, remember that Voyager will have passed through solar systems on timescales of tens of thousands of years. So on a timescale of 10 to the 9 years, Voyager will probably have already traveled through thousands of different solar systems. So why is this one different to Pioneer? Well, it will indeed get corroded. It will indeed, flying through the interstellar medium, end up unreadable. But this particular gold disk is protected behind a cover, and the cover is shown on the left-hand side there, which means the cover takes the brute force of the micrometeorite or the dust impacting on it, which ultimately will make the record itself completely unreadable after 1 billion years or so. The catch is, although the record is protected, and it's a normal phonograph with a stylus in which you turn it at a given speed and pick up the vibrations, The record will be protected for the best part of 1 billion years, even though the cover gets completely corroded and pitted. The downside is the cover contains the instructions for how to read the disk. But you could argue that if some extraterrestrial intelligence does pick this up after 1 billion years, even if they can't read the cover, they can probably figure it out. Surely they'll be clever enough to figure out there seems to be a groove in this thing. Let's see what these vibrations actually sound like when we convert them into sound.
Did it occur to anybody to put the same thing on the other side of that?
I don't think they're that worried about people picking it up after 1 billion years. What they did do, though, is to put some uranium in the cover so that anybody who picks it up can find how old it is by looking at the decay of the uranium. So at least they will know it's 1 billion years old, even if they can't actually read the disk. But I think people have assumed that if after 1 billion years they haven't been able to figure out how to read a record, then they don't deserve to listen to it. Still on a timescale of 1 billion years, we're now getting to the point where things are quite definitely going to change, because the sun has a finite lifetime. The sun is approximately 5 billion years old, and it's probably got 5 billion years ahead of it. But on timescales of 1 billion years or so, it is going to start to change on its journey towards being a red giant as the hydrogen fuel starts to run out. The sun's luminosity is going to increase. It's been estimated that its luminosity will increase something like 10% every billion years, another 10%, another 10%, another 10%. And given that the sun at the moment is just about enough to keep us at a reasonable warm temperature, as soon as the sun's output starts to increase, that means the Earth is going to be driven into a greenhouse effect, and the surface temperature will come up to a relatively balmy 80 Celsius. At this point, the oceans are going to basically boil dry, and we really need to find somewhere else to go. Going underground isn't really going to help. It'll still be just as hot. So we really need to leave the Earth and wait for it to cool down a bit and then come back later when it's done. The sun, as it goes towards its red giant phase, the sun is going to get larger and larger. And the surface of the sun is going to end up so large it will end up as being comparable to the orbit of the Earth. In other words, the sun's surface will come towards the Earth. And you could say, well, yeah, okay, isn't that going to be a bit of a problem? You think of that and you think, well, if the sun's surface is that close to us, regardless of whether it actually engulfs us or not, surely that's going to be a problem. But calculations differ, and not everybody is agreed on exactly what's going to happen when the sun swells up as a red giant. As the hydrogen is depleted, the hydrogen that's going to last for about 10 billion years or so, we're about halfway through its life. As the hydrogen gets used up, it's definitely going to swell, and it's been calculated that it will probably end up as a red giant about the size of the Earth's orbit. But as it goes towards its red giant phase, there's going to be a lot of solar wind. A lot of material is going to be leaving the surface of the sun. In other words, the sun's mass towards the end of its life is actually going to decrease somewhat. And if the sun loses mass, then there's less gravity pulling on the Earth, which means the Earth's orbit is going to increase. So this cartoon on the left shows that as the sun gets bigger, the Earth will actually move away from the sun. So yes, the sun is going to end up engulfing the orbit of where the Earth used to be. But by the time it gets there, the Earth might be where maybe Mars is now. And all the planets are going to move out because the sun loses mass, so all of the planets are going to end up moving out to larger radii. So it might be that the Earth gets engulfed, but it might be that the Earth survives. It's a rather tricky calculation to do to work out exactly what's going to happen in about 5 billion years or so. Let's assume it survives, just for the sake of it, rather than assuming that Earth is going to get engulfed. The sun will go through its red giant phase, it'll slough off its outer layers and generate a beautiful planetary nebula, which I guess we won't be able to see from inside it. And what's left is a white dwarf, something akin to a large lump of carbon. Some people say, might it not be a lump of diamond? Well, maybe, but it's going to be a large lump of carbon, which is what's left once the sun has used up essentially all of its fuel. Surviving the sun going through a red giant phase, you could argue, is a bit of, well, it's going to be a tough sort of few years going through that. But unfortunately, bad luck doesn't come individually. There's another bit of bad luck on a similar timescale. A few billion years after the sun has gone through red giant and gone back to being a white dwarf, the Earth is going to lose its magnetic field. Now, the Earth has a magnetic field because it has a rotating molten core, but the core is molten, not anything to do with the heat from the sun. It's to do with radioactive decay of elements in the Earth's core that have been there for 10 billion years or so. So eventually, those radioactive elements will not produce enough heat to keep the core molten. If the core freezes, we no longer have molten metal spinning, we no longer have a dynamo, we no longer have a magnetic field. When we lose the magnetic field, that means we're exposed to cosmic radiation. Cosmic rays will come flooding in. So that's going to be bad news. So even if we survive the sun going through the end of its life, we then have to put up with the fact that the Earth loses its magnetic field. It's thought that maybe this is what happened to Mars. Mars is a smaller planet. It would have cooled off faster than the Earth. So maybe Mars lost its magnetic field a long time ago. We think Mars had a magnetic field originally. Maybe Mars lost its magnetic field many billions of years ago, and as a consequence, it was then exposed to radiation, and that's what stripped its atmosphere. So maybe that's why Mars is substantially different from the Earth, simply because it's smaller and it cooled off faster. They say bad luck comes in threes. If we survive the sun going through a red giant phase, if we survive the loss of a magnetic field exposing us to cosmic radiation, we have another problem to deal with, and that is the Andromeda galaxy is going to come crashing into the Milky Way. Now, that's what it will look like in approximately 3.7 billion years or so. At the moment, the Andromeda galaxy is an easy target for a telephoto lens on a camera. It won't be long before you don't need a telephoto lens. You need a wide-angle lens because it's coming towards us, and it's going to get very, very large in our sky. When the two galaxies collide, there is going to be a riot of new star formation. It is not a cataclysm. Two galaxies colliding isn't the end of the galaxies. You could argue it's a sort of rebirth, because as the galaxies go through each other, basically the galaxies pass through each other. The stars themselves are very unlikely to hit another star. The gas will hit the gas, the dust will hit the dust. Individual stars will probably not hit each other. So the sun will probably come through this collision of galaxies unscathed. If it does end up getting ripped out of its location in the Milky Way, all of the planets will probably just go with it. But as the galaxies pass through each other, there'll be a short period while the galaxies separate, and then eventually they'll come back, and eventually they'll settle down into one mega galaxy. We're unfortunately going to lose the spiral arms that we have at the moment. So we see Andromeda galaxy as a beautiful spiral, the Milky Way as a spiral. Ultimately, when these two galaxies collide, the individual spiral arms will be ripped off, both of them. And we'll end up with two nuclei, the two supermassive black holes, one in the center of our galaxy, one in the center of Andromeda. Eventually, they will end up orbiting each other in this one. I don't know what you call this new galaxy. You can't call it the Milky Way anymore. You can't call it Andromeda. Milkdromeda? Andrilke? I don't know what you call this. We've got plenty of time to work out what the name is. We've got billions of years to figure that out, so that's not a problem. On a timescale of 10 to the 11 years into the future, the dance between the moon and the Earth finally comes to an end. This, by the way, is a genuine picture. It looks like a sort of Photoshop of the two. This is a genuine picture of the Earth and the moon, seen from quite some distance away. So we're looking at the far side of the moon, which of course is the side we don't normally see. That's why it looks rather odd and doesn't show the features that we normally expect. But by this length of time into the future, tidal locking has finally completed. The moon has been raising tides on the Earth raised tides on the moon, and here, one day is the same as 1 month. In other words, the length of time it takes the Earth to rotate once is the same as the length of time it takes the moon to go round the Earth. They will always face each other. So at the moment, we always see the same face of the moon, but it'll be the same in the opposite sense. The moon will always see the same face of the Earth. You'll find that there are some places on the Earth where the moon is simply stuck in the sky and never sets, and there'll be some places on Earth where the moon never rises in the sky. So in other words, it'll mirror what we've seen on the surface of the moon. That will now be on the surface of the Earth as they move together in lockstep, much the same way that Pluto and Charon currently do. They simply always face each other as they turn around their common center of gravity. We've said that in our local group, in our immediate neighborhood, there's the Milky Way right in the middle there. If we just blow that up a little bit, we find that the Milky Way is surrounded by lots of small galaxies, either dwarf galaxies or satellite galaxies. There are dozens, possibly hundreds of tiny galaxies around the Milky Way. Not only is the Andromeda galaxy going to come crashing into the Milky Way, but the Milky Way is going to hoover up all of these small galaxies as well. The entire so-called local group, the immediate vicinity of galaxies in our neighborhood, are all going to end up together. So the Milky Way and M31 and the Triangulum galaxy M33 are all going to merge into one mega galaxy. Okay, that's only a little icon. It's not actually going to be a spiral galaxy. It's going to be a large amorphous elliptical galaxy with no spiral arms. If that's going to happen on a timescale of 1 trillion years or so in the future, what about all the other galaxies? So that's only our immediate neighborhood. We are going to merge with Andromeda, but what about all the other galaxies out there in the universe? During a COVID lockdown, I tried to image a very distant galaxy. I called the short talk that goes with that Ancient Light, because during that lockdown, I tried to image a galaxy which was 25 billion light years away. This is a galaxy on the other side of the observable universe, but it's actually possible to photograph it with a camera without using a telescope. But what's even more amazing than simply the fact that a camera, a normal camera used to take pictures of lions and zebras and other things, can photograph a galaxy on the other side of the observable universe, is the fact that the galaxy itself was receding from us faster than the speed of light. Because of the expansion of the universe, this particular galaxy which I imaged is actually receding from us, and was receding from us when the light left it, at more than twice the speed of light. That is absolutely amazing. And when you think of images taken by, for instance, the Hubble telescope, it takes a little bit to realize that of those thousands of galaxies that you can see in an image like that, a lot of them are actually receding from us faster than the speed of light because of the expansion of the universe. That doesn't violate anything Einstein had to say. Einstein simply talked about how light travels through space, not how space expands and takes the galaxies with them. So at the moment, it is possible to see billions, if not trillions of galaxies. Of course, Hubble only has a relatively small field of view on the sky, but we deduce the existence of trillions of galaxies based on images like this and from the James Webb Space Telescope. And we know, or at least we have some comprehension of the universe by looking at images like this and figuring out some of those galaxies are close and some of those galaxies are far away. But on a timescale of this, 10 to the 12 years, the expansion of the universe will have continued and will have dragged galaxies so far away we will never be able to see them. In other words, if you imagine a civilization coming into existence on this timescale of 10 to the 12 years, imagine they built a Hubble Space Telescope and they asked themselves, what does the universe look like? They look out into the universe with their wonderful telescope, and what do they actually see? They see nothing other than the stars in their own galaxy. They don't see any of the galaxies that we would see because the expansion of the universe at this timescale has simply taken all of these objects too far away. So it's rather sobering to realize that even a very technologically advanced civilization in 1 trillion years' time would come to the conclusion that the entire universe is just their own galaxy. And they would have no idea that actually there are trillions of other galaxies out there. We are very lucky to live in a time period where we can actually see those galaxies because they will not be visible forever. Back in the beginning of everything, I tried to describe how the universe came into existence 13.8 billion years ago, and it took 3 minutes to make all of the hydrogen in the universe. In other words, after 3 minutes, all of the hydrogen was made, and then the universe continued to expand, and that hydrogen was spread everywhere, and that hydrogen has been used to make stars ever since. But after 1 trillion years or so, the hydrogen's running out. Can't last forever. If you take stars and convert hydrogen into helium and carbon and nitrogen and oxygen and phosphorus and calcium and all these other elements, the hydrogen is going to run out. Some people have said, well, yeah, we think you need hydrogen to make stars. That's the normal picture is you start with hydrogen, you let gravity collapse hydrogen clouds, the hydrogen gets compressed and you get nuclear fusion. Some people have said, well, maybe you don't need to start with hydrogen. Is it possible that you can start with something heavier, some other gas other than the lightest gas of all? So some people, some theorists have tried to do calculations and say, well, actually, maybe it's possible to start with a heavy gas. And you could end up with a star in which there are nuclear reactions in the core, but the surface temperature might end up being really low, possibly not thousands of degrees as it would be in the case of a red giant. Maybe it's only hundreds of degrees. Maybe it's possible to have nuclear fusion at the core, but ice in the upper atmosphere of a star, a frozen star. Is it possible to have a frozen star? Well, that's Disney's version of a frozen star. That's not what I'm talking about. If that's the picture you've got in your head, then let it go, because what I'm talking about is a star with fusion reactions in the core, but ice in the atmosphere. Some people say it might happen, other people say baloney. No, you absolutely do need hydrogen. You can't make stars out of anything but hydrogen. The mechanics, the thermodynamics, the physics just doesn't allow you to do that. So then you have a problem. And in order to discuss that, I have to change the scale on the top here. Notice the numbers have now flipped. Instead of talking about each box being 10 times further into the future, each box is now 1,000,000 times further into the future than the previous one. And we sort of start to run out of numbers to label these things. Is it a zillion years? Is it a gazillion? Is it a jillion? I don't know. Once you get above 1 trillion, it starts getting rather tricky to put labels on these things. So we'll just stick with the 10 to the power big numbers. So I've just said that if you start with a universe, after 3 minutes you've made all the hydrogen. If you then have lots and lots of stars, well, stars don't live forever. Some stars, especially the lightweight ones, the low mass stars, they can live definitely for trillions and trillions and trillions of years. But they don't live forever. So if the hydrogen runs out, what does that mean? There will come a time when there are no more stars shining. The age of starlight will come to an end. Those objects will still be there, orbiting around their galaxies, these zombie stars, white dwarfs, neutron stars, black holes. They are no longer any nuclear reactions at the core, producing energy which allows the stars to shine. White dwarfs start off white just because they're hot and they will cool off. Neutron stars haven't got any reactions in them, and black holes are black holes. White dwarfs, like our sun, when it comes to the end of its life, is probably just a lump of carbon and maybe a few other elements as well. So yes, they will start off hot, which is why they're called white dwarfs, because they start off at temperatures of many, many tens of thousands of degrees. But given time, they will simply cool off until they are black dwarfs, and they will be essentially invisible lumps of carbon. Some stars will be ejected from the galaxy. Some stars will be eaten by the supermassive black hole that we think exists at the center of what we can barely see, but we think at the center of every galaxy, we think there's a supermassive black hole. So when galaxies come to the end of their lives, some stars might be ejected, but ultimately a lot of the material, a lot of the dust, the gas, and the stars will be eaten by the central supermassive black hole. What happens to all the atoms in the universe? Well, subatomic physics, we don't really know what's going to happen, but we do know that at the moment atoms are made of a nucleus with protons and neutrons and a load of electrons buzzing around. And the real question is, are protons stable? Do protons live forever? And it's thought that protons may not live forever. If they do live, they probably live for this sort of length of time. But it might be that after this length of time, or on these sorts of timescales, protons decay into something else. And basically that means every atom in the universe will fall to pieces. If protons are stable, atoms will live forever. But if protons are unstable, then atoms will fall apart. The timescales, very much a matter of conjecture, because starting with where we are now, remember we're talking about 10 to the power 36, we're talking about ridiculous lengths of time into the future. It's very difficult to do calculations with any accuracy on these timescales. But even if protons don't decay, then atoms won't actually live forever, even if with proton decay, without proton decay, because the only atoms in the universe are in white dwarfs. There are no atoms in neutron stars, there are no atoms in black holes. So the atoms are in white dwarfs, and even they will end up evaporating until there's no atoms left. It's a quantum mechanical process that I'm not going to describe in any detail, but basically they will, if you like, fall apart and end up purely as radiation. The black holes themselves, remember, galaxies will collide with each other, and when galaxies collide, the supermassive black holes at the center of those galaxies will end up orbiting each other, and eventually they will spiral into each other and merge together as well. So large black holes like the supermassive black hole in the center of our galaxy, millions of solar masses, will combine with the one in Andromeda and then with other galaxies, and will end up with supermassive black holes of billions of solar masses. And there's no reason why they don't continue to coalesce until you get supermassive black holes with trillions of solar masses. But even black holes, which are essentially the only things left now, even they don't last forever. Black holes evaporate according to theories and conjecture which haven't been proved yet, but a lot of scientists think are fairly rock solid based on the principles. It looks like, according to Stephen Hawking, all black holes will evaporate. Okay, you have to wait for a really, really, really long time, which is why it's tricky. The amount that they radiate as they evaporate is very small, so we can't simply look at whatever black holes we can see at the moment and look for Hawking radiation because there's so little of it. But on these timescales, 10 to the silly numbers into the future, that radiation will eventually produce the evaporation of all of these black holes. As black holes evaporate, the radiation levels increase. The radiation levels depend on the mass. Really big black holes don't radiate very fast. Very small ones radiate a lot. So as they get smaller and smaller and smaller, they radiate more and more and more and faster and faster and faster until they finally disappear in a flash of radiation. The radiation isn't coming from inside the black hole, that's not allowed, but the radiation comes from just outside the surface of a black hole. This is what Stephen Hawking has conjectured, and it's now called Hawking radiation, even though it's not absolutely proven. It is thought to be a very likely situation on these timescales. Even the really big supermassive black holes will eventually evaporate, but on timescales that are even more silly. We've reached the end of this second timeline. Supermassive black holes will take substantially longer than even solar mass black holes. So we're talking about really, really big numbers. Have we reached the end of time? Well, you can't really define the end of time as such. But a useful number is simply to say, well, let's just imagine 10 to the power 100. 10 to the power 100 is a googol. Not that Google, that's a different Google. That's a misspelling. That's a misspelling of that Google. 10 to the power 100 is Google. And it's thought that on the timescale of a Google years, after 10 to the power 100 years, every last black hole in the universe will have gone. It's difficult to imagine, but the calculation, you can just do the maths. You can do the maths and you can figure out that on a time scale of 10 to the power 100, it doesn't look like there's any way that any black hole, i.e. any object, can survive beyond 10 to the power 100 years. So after this, nothing happens because there's nothing left. Every piece of matter in the universe has disappeared and has been converted into radiation. So there is just radiation floating around the universe as the universe continues to expand, and all that radiation gets stretched out to longer and longer and longer wavelengths. 10 to the power 100 is a silly number, and this is one of the few times I actually put all the numbers in, just to remind us what a silly number it is. It's 10,000 million, you can do it yourself. It's a lot of zeros. Imagining it is essentially impossible, but just because you can't imagine it doesn't mean you can't do the maths, and you can calculate how long does it take to evaporate, and you figure 10 to the power 100 years is about enough. So it looks like that's as close as possible as you can get to the end of everything, because nothing happens after this point. Is it eternity? Well, perhaps not, but eternity is a very long time, especially towards the end, as Woody Allen once said. But I prefer the XKCD version of thinking about how to put a sort of human slant on these ridiculously long times. The XKCD cartoon says a human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process, which apparently involves checking email quite a lot. So that's the depressing end of the universe. So let me finish on a slightly more upbeat note. You could argue that we live in a golden age because the sun is middle-aged and well-behaved. It's got a lifetime of about 10 billion years. It's about 5 billion years old. We're about halfway through. It's stable. It doesn't change much from day to day, month to month, year to year, decade to decade, millennium to millennium. The moon is at just the right distance to stabilize the Earth's axis and hence stabilize the Earth's seasons, which gives us a certain amount of regularity. It doesn't give us a uniform temperature, but it gives us a cycle that we can live to. As a sort of bonus, the moon is also at just the right distance to give us total eclipses of the sun every once in a while if you're lucky enough to stand at the right place at the right time. And thanks to evolution, we as humans are able to explore and discover and understand the universe in which we live. And we can do that by, for instance, building spacecraft and sending them out into the solar system to learn more about our immediate neighbors. And we can also build telescopes, which we can use to look out and see billions of galaxies at distances of billions of light years. And if you think of the time scale, we could not have done this in the early universe because we absolutely needed to have generation after generation after generation of stars to convert hydrogen into helium, helium into carbon, and nitrogen, and oxygen, and calcium, and phosphorus, and iron, and all of the elements that we need to make us, us. So you couldn't have existed in the very early universe. And we've just seen that the future is very dark and very boring. So you could say the best time to exist is now. Thank you for listening.